Hey, welcome back. This is Mr. Jorgens here. We're going to build on what we did yesterday. Yesterday we talked about solving one-step equations, and today we're going to build off of that and start solving some two-step equations. You've done this before in junior high, but this should be a good review for you. The first two math problems we're going to look at today are just to remind you what we did yesterday. Yesterday we talked about solving one-step equations. Our process for solving one-step equations is to identify the operation and then undo it or inverse it using its opposite. So in our first problem here, I have x plus 3 equals 7. Now the first thing I'm going to do is I'm going to identify the operation. In this case, the operation is add 3 because the number that's stuck to x is an add 3. Now the opposite of addition is subtraction. We learned that addition and subtraction are pairs and multiplication and division are pairs. So the opposite of adding 3 would be to subtract 3 onto both sides. I like to draw that line there to keep both sides balanced. Because in math, if we're ever going to subtract 3 off of one side of an equation, we have to also subtract 3 off of the opposite side of the equation. Add 3 and subtract 3 are inverses. So x plus 3 subtract 3 cancels, and I'm just left with x on the left-hand side. On the right-hand side, 7 subtract 3 makes 4. So my answer would be x equals 4. Hopefully this makes sense to you, because if you plug that answer back into our original equation, 4 would replace x. So when I replace x with 4, I'd be left with 4 plus 3, which does equal 7. In my second equation, it may be more difficult for you to see what the operation is or how that 5 is connected to x. But we have to think, is that 5 connected to x by adding, subtracting, multiplying, or dividing? In this case, that 5 is stuck to x by multiplying. If we don't see any sign, like in this first one here, we saw the plus sign, right? So if there's the plus sign there, then we know it's add. If there's no sign, it's just 5x or a number right in front of x, we know there's an invisible multiplication dot there. And we can undo that multiply 5 by its opposite, which would be dividing 5 off of both sides. On the left-hand side, when I divide by 5, 5 divided by 5 just makes 1x. So the two 5s cancel or undo each other. On the right-hand side, 30 divided by 5 makes 6. So my answer would be x equals 6. This should make sense to you because I have 5 invisible multiplication dot x. So 5 multiplication x, in this case, would be 5 multiply 6. And 5 times 6 does make 30. That should be a quick review of what we did yesterday. Today, we're going to do the same thing, except there's going to be 2 numbers that we have to undo instead of just 1. Our first example from section 1.2 is the following. 2x plus 3 equals 11. Now, the main difference between this problem and a problem we would have seen in section 1.1 is instead of just one number on the same side as x, we have 2 different numbers, the 2 and the 3. We know we want to get x by itself because we want to figure out what that number is. We know 2 multiplied by some number plus 3 makes 11. So if we want to figure out what that number x is, we have to move both the 2 and the 3. The hard part is we have to figure whether we should subtract 3 first or divide by 2 first, because depending on the order you go in, you'll get a different answer. Now, the way we're going to know what order to go in is by undoing PEMDAS in reverse. PEMDAS stands for parentheses, exponents, multiply and divide, and add and subtract. In this case, our 3 would be in the add and subtract level, and our 2 would be in the multiply and divide level. So 3 is lower. So whatever comes lower in PEMDAS, we're undoing operations here. So since we're undoing them, we're going to go in reverse. In this case, that 3 is lower, so we're going to know that we need to move the 3 first. We can undo adding 3 by subtracting 3 from both sides. In this case, 11 subtract 3 is going to make 8. Add 3 and subtract 3 is an inverse, so it cancels. And we're just left with 2x on the left-hand side. Next, we have to undo the 2. And the 2 is stuck by that invisible multiplication dot. Remember, if you ever see a number stuck directly in front of x, we know it's stuck by an invisible multiplication dot. And we can undo that multiply 2 by dividing 2. And the 2 comes above the 3, so we know we're going to do the 3 first, and once we do that, then we're going to move the 2. And we can move that by dividing both sides by 2. Again, that fraction bar means division. Division and fractions are related. 8 divided by 2 makes 4 on the right-hand side, and 2 divided by 2 makes 1x, and we can just write 1x as just x. So we're left with our answer, x equals 4. If I think about what that means in the context of this problem, I was looking for a number, right? So I was looking for 2 multiplied by some number, and I'm saying that number is 4. Add 3, which is supposed to make 11. 2 multiply 4 makes 8, and 8 plus 3 does make 11. So picking 4 as my number there works, because if I multiply by 2 and then add 3, I'm left with 11. Here's a second example. We have x divided by 3 plus 7 equals 5. And I'm very careful to read that as x divided by 3, because every symbol has to either be add, subtract, multiply, or divide for us today. And we need to be very clear about which operations we have. Now, I want to get x by itself. That's my goal in all of these problems. In order to do that, in this case, I have to move the 3 and the 7. The tricky part of these problems is figuring out which one I'm going to move first. Now, if you remember from our first example, the order is going to be determined by undoing PEMDAS in reverse. The 3 is stuck to x by division. The 7 is stuck to x by addition. This means if I'm undoing PEMDAS in reverse, I'm going to move the 7 first and the 3 second. If I go to move the 7 first, I'm going to undo addition. The opposite of addition is subtraction. So I'm going to undo add 7 by subtracting 7 from both sides. Add 7 and subtract 7 are inverses, so those parts cancel. And we're left with just x divided by 3 on the left-hand side of the equation. The right-hand side is a little bit trickier. Think to yourself for a second. 5 subtract 7. What would 5 subtract 7 make? All right, hopefully now that you had a chance to think about it, you realize that 5 subtract 7 makes negative 2. The way I like to think about it is by using a plus-minus chart. So whenever I do subtraction and adding negatives and I get confused, is it positive 2, negative 2, is it 12, negative 12, I'm confused, I make this plus-minus chart. The first number 5 is positive, so I'm going to put 5 next to my plus. The second number 7 is negative, so I'm going to put 7 next to the minus. Then I ask myself 2 questions. The first question is which has more? In this case, the negative has more, so I know my answer is going to be negative. After I ask myself which has more, I ask how many more are there? In this case, 7 is 2 more than 5, so there's 2 more negatives than positives. So I know that the answer is going to be negative 2. Another way you can think about that is by listing 5 positives and 7 negatives, and each plus minus pair makes a 0 pair. After I collect all my 0 pairs, which makes 0, I'm left with 2 negatives, or negative 2. Now that I've determined that 5 subtract 7 makes negative 2, I'm left to undo my divide 3, because I know I have x divide 3 makes negative 2. I can undo division by multiplication, so I'm going to multiply by 3 on both sides. Now I'm going to multiply by 3 because I know that multiply 3 and divide 3 makes 1, or 1x. So they cancel each other on the left-hand side. And I'm left with x equals, and then negative 2 multiplied by 3 makes a negative 6. And the reason why negative 2 times 3 makes negative 6 is based on something I like to call the multiplication triangle for multiplication and division. When you're adding and subtracting with negatives, you use the plus minus chart that I showed on the left with 5 and 7. When you're multiplying and dividing with negatives, you use this multiplication triangle. In this case, I had a negative times a positive. Since I had a negative times a positive, the corner that's left over is a negative, so I know my answer is going to be negative. So I know my answer is x equals negative 6. If I think about what that means in the original problem, I was looking for some number divided by 3. So I'm saying that number divided by 3 and then add 7. Negative 6 divide 3 makes positive 2, or sorry, negative 2. And negative 2 plus 7 makes 5, which is what we wanted in our original problem. So I know that my answer is x equals negative 6. Here's 2 for you to try on your own. Make sure to show your work on a separate sheet of paper. Go ahead and check your work on the first try these question. On this one, we needed to move the 7 first and the 2 second. When we subtract 7, 17 subtract 7 makes 10. Then afterwards, when we divide 2, 10 divided 2 makes 5. Now go ahead and try the second question if you haven't already. Enter your answer when you're ready. Now you can check your work on the second question. On this problem, you should have moved the 4 first, because when we move that 4, it's going to undo and add 4, and we can undo that by subtracting. 13 subtract 4 makes 9. Then I can undo my divide 3 by multiplying by 3 to both sides. And 9 multiplied 3 gives my answer of 27. Good work. You made it through the first day of 1.2. I know this stuff can be tricky at times. Keep working hard. And we're going to look at the second day of section 1.2 tomorrow.